Let's continue from the previous class. So let's look at example 1. You have to determine the maximum pressure as well as the braking torque. The axial force is given as 4 kN. The inside radius is given as 50 mm and the outside radius is given as 100 mm. You have to take into account that we are dealing with a uniform wear case, and the coefficient of friction is given as 0.4. So uniform wear, the equations are equations 1, 2 and 3. So actuating force is given. We know our inner diameter, we know our outer diameter, so we can make Pmax the subject of the formula. So your maximum pressure is equal to 2 times the actuating force divided by pi inner diameter multiplied to outer diameter minus the inner diameter. So once you substitute all of these values, you should end up with a value of 254.65 kilopascal. So now what happens is, when we're looking at torque, we can use equation 2 or equation 3. So what happens is, you can use both these equations depending on the parameters that are given to you, and you can always verify your solution. So torque is nothing but F pi P max D divided by 8 into outer diameter squared minus inner diameter squared. So coefficient of friction was given as 0.4. The maximum lining pressure you have calculated from here, so substitute it over here. The inner diameter is 0.1, the outer diameter is 0.2. So substitute everything into this equation and you should end up with a value of your torque being 120 Newton meter. You can also use this equation. You can use also this equation to verify. So Fi was given, all these variables were given in the problem. You're not solving for anything. So once you substitute all of these values, you get a torque value of 120 Newton meter. However, in this equation, you were to find Pmax. So you have found your Pmax. So this actually serves as a verification process. If your Pmax was wrong here, this value and this value would not tally up. The sole reason is that the values over here were already given, so you're not solving. So you can verify your solution of your Pmax just by comparing these two values. So now let's move on to example 2. It says that a clutch plate having a single driving plate with contact surfaces on each side is required to transmit 110 kilowatt of power at a speed of 1250 revolutions per minute. The outer diameter of the contact surface is to be 300 mm. The coefficient of friction is given as 0.4. You have to determine the inner diameter of the contact surface, assuming uniform pressure of 170 kilopascal. So in this case, we having a case in which we have a uniform pressure. So these variables are given. So this time around we're looking at a uniform pressure. So the equations that we are going to use are going to be with respect to the uniform pressure cases. So equations 4, 5 and 6. So we given power, we've given the rotational speed. So power is nothing but tau omega. So power is nothing but your torque times your angular velocity, and angular velocity is given as 2 pi n upon 60. So power is given as 110 kilowatt. Your speed was given as 1250. So we can simply calculate our torque. So you can calculate your torque using this expression, or what you can do is you can calculate your angular velocity, and that angular velocity divided by the power will give you your torque. So your torque equates to 840.34 Newton meter. So now what happens is, most of you will be asking me as to why I have a 2 over here in this expression. So let's go back to the question. It says that a plate clutch having a single driving plate with contact surfaces on each side. So what it simply means is that the clutch is effective on both the sides. So you have a single plate. Let's assume, and it is effective on both the sides. So effective on both the sides. So that means is that your contact surfaces are 1 and 2. So that's why I have 2 over here. This formula is again for a uniform pressure case. So torque we have calculated, done. F is your coefficient of friction, Pmax is your maximum lining pressure. So what we have is, we know our outer diameter, but we have to find our inner diameter. So what we have is we can make our inner diameter the subject of the formula. So the first thing is that d cube minus outer diameter cube minus inner diameter cube is nothing but equals to this, and we can find our inner diameter using this expression. So you substitute all the values step by step, and you should end up with a value of 150 mm. So the inner diameter is 150 mm. So once again, this expression seems to be difficult, but what I'm doing is I'm substituting all the values over here step by step and making the inner diameter the subject of the formula. So you can leave your answer in meters or you can convert it to millimeters. It really does not matter. Now let's move on to multiple disc clutch. So what generally happens is we will look at why multiple disc clutches are used and maybe look at a simple example. So in this diagram you'll see that you've got multiple discs that are part of the driving shaft as well as the driven shaft. Disc A are constrained to rotate with the input shaft. So these are your disc I over here. So 1, 2, 3 and 4, and disc B are constrained to rotate with the output shaft or the driven shaft. So one of the things which are important here is that if I give you that on a driving shaft you've got 3 discs, on the driven shaft you've got 2 discs. So how do you calculate the number of effective surfaces? So it's quite easy. What you do is, let's say if M is the number of if M is equal to the number of discs on your driving and N is equals to the number of discs on your driven. So what generally happens is the number of friction surfaces that we'll have is simply M plus N minus 1. So the number of friction surfaces that we'll have is simply equal to the number of discs on the driving shaft M plus the number of discs on the driven shaft N, and that subtract 1 to it. So in this case what we have is we have 1, 2, 3, 4 discs on the driving shaft, and we've got 3 discs on the driven shaft. So can you tell me how many friction surfaces you have? So 4 plus 3 is 7. 7 minus 1 is 6 contact surfaces. So let's see where we actually end up with 6 contact surfaces. So the first contact surface is over here. So 1. The other one is here. 2, 3, 4, 5 and 6. So again, in order to calculate the number of friction surfaces you have in multiple disc clutches, it is basically the sum of the number of discs on the driving plus the number of discs on the driven. Whatever value you get, subtract 1 from it, and that's the number of effective friction surfaces that we have. So the next thing is we need to understand as to why multiple disc clutches are used. So the disc freely slide axially when the clutch is disengaged. When the clutch is engaged, the discs are clamped tightly together and provide driving surfaces. A multiple disc clutch is used when a large torque is to be transmitted, and application is extensively used in motor cars and machine tools. So sometimes you would be asked to justify why multiple disc clutches are used. A very simple reason is that we have already looked at disc clutches. So we know if we want to increase the torque that is transmitted by a single disc clutch, what we need to do is we need to physically increase the dimension of the clutch plate. So increasing the outer diameter and or maybe decreasing the inner diameter. So the larger the friction surface we have, the more torque it transmits. So one of the problem is that, for instance, you are required for a machinery that in the beginning it was able to cater for a torque transmission of, let's say, 100 Newton meter. Now for that same machine, the requirements have increased and you are required to transmit 150 Newton meter. So you've got several options. You will change the clutch system entirely. So previously you had a smaller clutch system, so to transmit larger torque you might need to use a larger clutch system setup. So that's one. And what generally happens is, if we use a single disc clutch, generally the geometry or the dimensions of the clutch system increases. So sometimes space could be an issue. So for that reason, what we do is, instead of using a single disc clutch system, we use multiple disc clutch systems. So effectively within the same geometry, by having multiple plates, we will be able to increase the torque that is transferred by the clutch system. So that's the reason as to why we use multiple disc clutches. The other thing is, multiple disc clutches systems are compact and they are able to transmit more power compared to a comparable size disc clutch. So now let's just look at example 3, which is talking about transmission of torque and power using a multiple disc clutch. So a plate clutch has 3 discs on the driving shaft and 2 discs on the driven shaft. So number of discs on the driving shaft M is 3, number of discs on the driven shaft N is 2. The outer and inner diameter of the contact surfaces is 240 mm and 120 mm respectively. Assuming uniform pressure and the coefficient of friction is 0.3, you have to find the axial force if the power transmitted is 25 kilowatt at a speed of 1575 revolutions per minute. So what we have is, we have a case where we've got uniform pressure. So we will again refer to our equations for uniform pressure. So power was given as 25 kilowatt and the speed at which the clutch is rotating was 1575 revolutions per minute. So again we can calculate our torque. So power is equals to torque times our angular velocity over here. So what we can do is, we can simply calculate our torque. So substituting, you will end up with the value of 151.58 Newton meter. Now what happens is, again we can calculate our torque, because we can calculate our torque, but this time around we need to calculate our actuating force. So use equation from your uniform pressure case in which torque and actuating force are related. Now what happens is, you'll see that I have N over here, because in this case we've got a multiple disc clutch system. So we had to calculate the number of friction surfaces. So total number of discs on the driving was 3, total number of discs on the driven were 2. So 3 plus 2 is 5, 5 minus 1, 4. So we've got effectively 4 friction surfaces. This is how I end up with a value of 4 over there. So now what we have is, actuating force we are finding. Coefficient of friction was given as 0.3. The outer and the inner diameters were 0.24 and 0.12 meters respectively. So if you make Fa the subject of the formula, you should end up with the value of 1353.39 Newton as your actuating force.